Direct, analytical tone. Every device on a network requires an identity to route traffic. When thousands of transient devices connect and disconnect, mathematically negotiating these identities without causing IP collisions becomes a massive logistical problem. At the hardware level, devices are permanently identified by their MAC addresses. IP networks dictate a strict separation of that physical identity from the logical routing identity, the IP address. In early network environments, administrators mapped these identities manually or relied on the Bootstrap Protocol, known as Boot. Boot lacked a mechanism for dynamic reuse. Once an IP was tied to a MAC address in the database, it stayed there, rapidly exhausting available address pools as environments expanded. Standardized in the early 1990s, the Dynamic Host Configuration Protocol solved this through a centralized allocation system based on the concept of the lease. This allowed networks to automatically reclaim and reallocate addresses as soon as devices disconnected. To understand how this protocol operates at scale, we have to examine its packet headers, the logic of its relay agents, and the security frameworks it enables in enterprise environments. DHCP operates as a strict finite state machine, governing routing logic, network boundaries, and high availability across the entire infrastructure. The DHCP v4 header uses UDP with strict port separation, servers on port 67, clients on 68. Phase 1 is Discover. A client initializes at 0.0.0.0 and broadcasts a DHCP Discover to 255.255.255.255. It places a random number in the XID field to match server replies. In Phase 2, servers receiving this broadcast check their local pools and respond with a DHCP offer containing a proposed IP address. This proposed address is populated directly into the yiaddr, or your IP, field of the returning packet. During Phase 3, the client officially selects one of these offers and broadcasts a DHCP request. This broadcast request simultaneously confirms acceptance with the chosen server and signals others to release their reserved IPs. Finally, in Phase 4, the selected server confirms the lease with a DHCP ACK. This uses the options field to deliver final parameters, like default gateways and DNS. This four-step DORA sequence guarantees a mathematically sound handshake, keeping every participant perfectly synchronized on the current state of the address pool. A client's IP behavior is governed by a finite state machine. The device enters the bound state, and the lease clock begins counting down. To maintain connectivity, the T1 timer triggers at 50% of the lease duration, shifting the client into the renewing state. The client attempts to unicast a DHCP request back to its original server. If unreachable, the T2 failsafe triggers at 87.5%. The client enters the rebinding state, broadcasting its request. If the entire lease expires without renewal, it drops the IP and returns to init. The only exception is the init reboot state. A restarting device with an unexpired lease can skip the initial discovery phase and immediately broadcast a request for its previously held IP, minimizing connectivity delays during system reboots. By enforcing these strict timers, the finite state machine forcefully ages out disconnected devices. This continuously reclaims limited subnet space without requiring any manual intervention. While the DORA process works flawlessly on a local segment, IP architecture dictates that broadcast traffic cannot cross Layer 3 boundaries, like routers. To scale a single DHCP server pool across multiple remote subnets, networks utilize a DHCP relay agent, a configuration applied to the local gateway that intercepts UDP port 67 broadcasts. The relay agent converts chaotic broadcasts into organized unicast packets, routing them to the centralized server cluster. Before forwarding, the relay injects its own interface IP address into the yiaddr, or gateway IP address field of the packet header. The server reads this yiaddr field to deduce exactly which remote subnet the client resides on, ensuring it assigns an IP from the correct pool. In massive enterprise environments, access switches provide the server with even more physical context using Option 82, the Relay Agent Information option. Option 82 inserts specific suboptions, the circuit ID and remote ID. These allow administrators to tie IP address assignments directly to specific physical switch ports or VLANs, preventing users from sharing connections. This targeted delivery is necessary for complex end devices, like VoIP phones, which rely on specialized DHCP options from relate scopes to locate their configuration servers. By leveraging relay agents and option 82, a single centralized server team can seamlessly administer thousands of disparate physical subnets. As networks transition to IPv6, the protocol requires a structural rewrite to handle the massive expansion in scale, DHCP v6. DHCP v6 completely eliminates broadcast traffic. It relies entirely on targeted multicast addressing, and it abandons hardware MAC address tracking in favor of a DHCP unique identifier, or DUID. The legacy IPv4 DORA handshake is replaced by the four-message SAR exchange: solicit, advertise, request, and reply. IPv6 introduces stateless DHCP v6 mode. Clients generate their own IP addresses using stateless address auto-configuration, querying the DHCP server only for auxiliary parameters like DNS. Whether using IPv4 or IPv6, DHCP is a mission-critical service. To prevent a single point of failure, enterprise servers utilize the RFC 8156 failover protocol to synchronize their state data in real time. This redundancy relies on the maximum client lead time. If the link between servers breaks, this strict buffer dictates how long leases are extended. It mathematically prevents a split-brain scenario where both disconnected servers blindly assign the same IP address to different clients. The integration of multicast communication and synchronized failover protocols reflects the evolution from best-effort local area networks to hyperscale, zero-downtime infrastructures. Despite its structural logic, the original DHCP specification lacks built-in authentication. This leaves the local network vulnerable to rogue server attacks, where a malicious node intercepts discovery broadcasts and assigns fraudulent gateways to intercept traffic. To secure the network access layer, administrators implement a mitigation framework on the local switches known as DHCP snooping. DHCP snooping categorizes physical ports as trusted for servers or untrusted for users. The switch actively drops any server replies from untrusted ports. As leases complete the DORA process, the switch dynamically compiles a DHCP binding table, mapping every MAC, IP, and port in real time. This binding table serves as the mandatory validation database for the local network fabric. It powers advanced security mechanisms like dynamic ARP inspection and IP source guard, actively dropping traffic from devices attempting to spoof addresses they weren't assigned. The protocol functions as the primary state synchronization mechanism for the network access layer. By mastering its header mechanics, state machine timers, and binding tables, engineers build the secure, automated foundation required for modern software-defined architectures.